A dual-homed end station leads a good life until one of the leaf switches it is connected to loses its uplink connection. This can result in some traffic taking suboptimal path or worse, traffic black holing. But there is a way to fix that, and that's what I will show you in this. So in what scenario we can face traffic black holing for a dual-homed end station on the loss of uplinks on only one of the leaf switches it is connected to? Consider this scenario. Here endpoint 1 is dual-homed end station connected to both leaf 1 and leaf 2. In this topology, we are running OSPF as underlay protocol and VXLAN EVPN as overlay. And there is no route pairing directly between leaf 1 and leaf 2. As you can see, leaf 1 is the MC lag active pair and leaf 2 is the MC lag standby pair. Now, if leaf 1 loses its uplink to spine, it has also lost its peer keep alive link to leaf 2, because this was the link leaf 1 was using, leaf 1 and 2 were using to send their keep alive messages. Now, when leaf 2 can see that peer link is still up, but peer keep alive link is down, because it is MC lag standby peer, it will shut down all of its downstream MC lag interfaces. Now that is a nightmare situation, because traffic from endpoint 1 will hit leaf 1, which does not have any uplink, and traffic will be black holed. Well, I hope you can see how to fix that as well. Simply create a direct OSPF route pairing between leaf 1 and leaf 2 so they can learn underlay routes over this peer link as well. Now your traffic from endpoint 1 can seamlessly reach leaf through leaf 2 to endpoint 2 as well. But is this the most optimal path? Please note that when we have this direct OSPF pairing between leaf 1 and leaf 2, your peer keep alive link will never go down, which means that both of these links between endpoint 1 and leaf 1 and leaf 2, both of these links will remain up. So definitely we are not using the most optimal path between endpoint 1 and endpoint 2 for communication. So how we can fix that? Answer is, we can fix it by configuring something called link state tracking. The way it works is that we will be tracking the state of our uplink ports. And in this example, when leaf 1 loses its uplinks, it will automatically shut down its downstream MC lag links as well. So now there is only one path available for endpoint 1 to communicate with endpoint 2, and that is the best available optimal path. Wonderful, useful feature, isn't it? So how do we configure it? We can configure it in 2 steps. In step number 1, we create a link state track group in global configuration mode. So we are instructing it to take effect on all downstream ports which are part of an MC lag. So single attached devices won't be affected. And in step 2, we are identifying our uplink ports and map them to this track group we created in the previous step. Here is an example. So we create a group called uplinks. We go to our uplink port, which is Ethernet 56 in this case, and we map this interface to the group we created in the previous step. This is how we do the verification, and we will do our verification in the lab section. So this is our lab topology. And we have already configured OSPF between leaf 1 and leaf 2. So we won't be seeing any traffic black holing, the first scenario I discussed earlier. But we can still face suboptimal routing scenario. So let me quickly show you my OSPF pairing. So on leaf 1, I have two OSPF pairs. So 0.4 is my neighbor through Ethernet 56, which is spine 1, and 0.2, which is the loopback for leaf 2, and I'm pairing it over VLAN 998. So that's my transit VLAN between leaf 1 and leaf 2, which uses this peer link. Okay, this is my end station, which is connected to both the leaves on port channel 1. So if I do show port channel summary, you can see we have this port channel 1 and show MC lag brief will show that leaf 1 is active and port channel 1 is basically an MC lag. So MC lag brief on leaf 2, you can see it is standby, and MC lag port channel 1 is up. Okay, so here we are already running all the BGP, EVPN configuration, OSPF configuration. All of this is done. So we should be able to ping from this endpoint 1 to endpoint 2. So if I go to endpoint 1, which is also a switch, if I do show IP route, as I said, this is also a switch. So you can see that I've configured an IP 10.1.1 here, and its default gateway is 10.1.1.254. So if I ping 254, this is basically the SVI on VLAN 10. So run interface VLAN 10. It's in VRF1, and similarly, if I do show, VLAN 10 configuration, you can see same IP configured on the leaf 1 side, as you would expect in an MC lag scenario, in the logical VTEP scenario. Okay, so if I show IP route, my VRF1 table, you can see this endpoint 2, 200, 200, 200 is already learned through 100.3.3.3, which is basically the VTEP IP of leaf 3. And VTEP IPs we learn to underlay, show IP route, which should be in the default routing table. So you can see 100.3.3 is reachable over Ethernet 56 through the spine. So all the routing, all the control plane looks good. If I ping endpoint 2 from my endpoint 1, I can ping. So from here to here, I can ping. The first thing I want to find out is that out of these two available links, which of the link endpoint 1 is using? And then I will shut down that uplink to show you this suboptimal routing. So I will create some ping traffic. Maybe I should send 50. Now, one easy way to figure it out would be, for example, if I go to leaf 2, I can go to my click mode, which is the Linux shell, and I can do a TCP dump on VLAN 10, because that is the default gateway for endpoint 1. I don't see anything here, so it's probably using leaf 1. I'll go to click mode, sudo TCP dump -i and VLAN 10. And yes, you can see that both incoming and outgoing traffic at the moment is using this link, which means it is going out of Ethernet 56. Okay, so what I'll do now is I will shut down Ethernet 56 and see what difference it makes. Should probably generate some more traffic. Okay, so it should still be hitting leaf 1. Let's go to leaf 1 and go to Sonic CLI mode, and I will shut down my interface 56. Shut down. Any difference to the traffic? No, it is still ongoing. Ping is still working. How? Because now I should be using this link between leaf 1 and leaf 2. So if I go to leaf 1, do a do show IP route, you can see now it is saying 100.3.3 is reachable over VLAN 998. So the traffic is coming this way, going over VLAN 998 to leaf 2 and getting to its destination. Is this the optimal path? Answer is no. For example, if I go to leaf 2, still nothing in TCP dumps, no traffic is coming this way. And if I do show port channel summary, you can see that this port channel, this link is still up. So this link is available, but still our traffic is going through leaf 1 to leaf 2 is suboptimal path. We can avoid this by configuring link state tracking. And the way we do it is, once it is configured, as soon as this Ethernet 56 is down, this link will go down as well, and all the traffic will flow through the best available path. Let's do this configuration. So I will only show you this configuration on leaf 1. In a live scenario, in a production environment, obviously we'll configure it on both the switches, both on MCLAG peers. Okay, and if I do my verification, so I can do show link state tracking. So it tells me that a link state track, a group called Uplinks is configured, and I can get a bit more information by looking for this particular uplink. So it tells me that this is configured, and for downstream it will be port channel 1. Okay. Timeout 60, I'll talk about it later, what it means. Okay, so now let's go to our interface. And map it. So the command will be link state tracking uplinks. No, sorry, uplinks, and then I need to tell that this is my upstream link. And that's it. Show link state tracking uplinks, and it tells me that Ethernet 56 is configured. Okay, and did you notice that it has also already disabled port channel 1 because Ethernet 56 was down and it was being tracked. It has disabled port channel 1. Okay, let's bring it up, and then we can send some traffic and we can bring it down again. So interface Ethernet 56, no shutdown. Now, if I do show link state tracking Ethernet 56 is up, but port channel 1 still seems disabled. Why? This is up. Why this is still down? Because there is a timeout of 60 seconds. So when the uplink comes back up, we are not going to bring all the downstream links at the same time. We're going to give it some time to settle, to synchronize, to converge. And that time is configurable. By default, it is 60 seconds. So show port channel summary will show you that it is down, and within a minute it will come back up. Okay, so it's been 1 minute now. So if we now run this show link state tracking uplinks command, we can see that Ethernet 56 as well as port channel 1 is up. Right, the last thing now we want to do is we will start sending some traffic from endpoint again, and this time when we will shut down Ethernet 56, we will see that port channel 1 will be shut down straight away as well, and we will see that the traffic will move to leaf 2, and we will not see any traffic drop, and we won't be doing any suboptimal routing either. So let's do that. Generate some traffic from endpoint, and let's verify if leaf 1 is still receiving this traffic. So TCP dump. Yes, I can see both outgoing as well as incoming traffic is using leaf 1. And now I will go to my interface, my uplink, and shut it down. There we go. If I come back to my leaf, my endpoint, it is still successfully pinging, so no traffic drop at all. And on leaf 1, if I do show, if I show the group, show link state tracking, we can see this is disabled. And if we go now to our leaf 2, and do a TCP dump, is the traffic still flowing? No, but you can see that we did a shutdown and we did not see any traffic loss at all. And now obviously all the traffic should be flowing through leaf 2. So as you can see, now the traffic is using leaf 2 for communication. So that's all from this lab. This is how we can configure link state tracking on Enterprise Sonic to avoid suboptimal routing for a dual attached host. As always, if there are any questions, please ask in the comment section. Otherwise, we'll see you in the next